All right, so L.4 or limits 4 is about trig limits and the squeeze theorem, and we're going to actually start with the squeeze theorem. Usually the named theorems are ones that you really need to know for just in general, but for the AP exam if you're taking AP. The squeeze theorem is not necessarily one of those. We've seen it on the AP exam before, actually once or twice. I think it's been on in recent years, but typically it's not tested that much. So this is one you could get by with maybe not knowing as well. It's also known as the Sandwich Theorem or the drunk guy walking between two policemen theorem, and you'll see why in a second, why it's called that. But they actually accepted that on the AP exam as the name of the theorem. So here's the theorem, so this is the condition that has to be met. If g of x is less than or equal to f of x is less than or equal to h of x for all x not equal to c, so all x except c, in some interval around c. So it doesn't have to be for all x. It just needs to be in some small interval around c. All right. Usually we come up with something that works for all x's, but in case you can't. And the limit as x goes to c of g of x equals the limit as x goes to c of h of x, and equals, they both equal L. Then the limit as x goes to c of f of x equals L. How this is used a lot, and this explains the whole drunk guy walking, is that you have some sort of functions, and a lot of times, for whatever reason, I've seen, we aren't going to use it on the example, but I've seen absolute value used a lot. Absolute value and negative absolute value. All right, so a v and an upside down v. This would be absolute value. This would be negative absolute value. And then you have some function that's between them. So usually it's kind of a trig type function that is oscillating. So maybe like this wouldn't work with sine 1 over x, but it'd be something like that. Maybe that's what this one looks like. I don't know. I haven't graphed it. But it's oscillating, but it's trapped between those two functions. And so that's what this is saying, is you've got some function that's trapped between these other two functions. All right, and so you can find the limit of the absolute value of x and negative absolute value of x as x goes to 0. It obviously goes to 0. They meet at that point there. And so if those limits both are 0, then it's squeezing that other function down to 0. So no matter how much it's oscillating in here, it's going to get squeezed down to 0 if it's bounded by those functions. So that's where you get drunk guy walking between two policemen theorem, because you've got the two kind of policemen here and the drunk guy is wandering back and forth between them. And they are herding him into a cell or a car. I don't know. But I thought that was funny when we graded that. Somebody had that written down. But anyway, so we're going to do this limit as an example of squeeze theorem, of using squeeze theorem. So the limit as x goes to 0 of x squared sine 1 over x squared. So the deal with this one is if you plug in 0, you have 0 times the sine of 1 over 0. And 1 over 0 we typically think of as infinity. But what's the sine of infinity? We don't know. So what we can do, though, is if we just work with sine, let's just consider that part of it. All right, sine and cosine are always between negative 1 and 1. All right, so negative 1 is less than or equal to sine of 1 over x squared, which is less than or equal to 1. All right, this is true for all x's. All right, sine is trapped between negative 1 and 1. That's just what it is. All right, remember our sine function, we went over that. The highest it gets is negative 1, the lowest it gets is positive 1. So that is true for all x. We have x squared, so let's just take everything times x squared. So this is going to be negative x squared is less than or equal to x squared sine 1 over x squared is less than or equal to x squared. All right, so we now have this. All right, we have our g of x, our h of x. This is our g, this is our h, this is f. And it's true for all x's. All right, it happens to be true for all x's, not just an interval around 0. And we need these two limits to be the same. So we're taking the limit as x goes to 0 based off of the problem. So let's take the limit as x goes to 0 of negative x squared. If you plug in 0, that's negative 0, which is 0. And the limit as x goes to 0 of x squared is also 0. So since these are the same, they're both 0, then the limit as x goes to 0 of x squared sine 1 over x squared is also equal to 0. So we'd say therefore, these 3 dots in a triangle mean therefore the limit equals 0. Okay, so that's how you use squeeze theorem. You have to come up with two functions that bound the function you're looking at, and for a trig function that's typically pretty easy. And then you have to show that the limit of the two boundary functions are the same. All right, and if that all works, if you have this set up and you have these two limits being the same, then the limit of the function you're looking for is the same as the other two limits. Okay, so that's the big deal with the squeeze theorem. There's one more theorem, and this is a kind of important one, especially the sine x over x one. You can prove this one. I could prove it for you, but I don't want to waste the time doing it, and most people wouldn't be interested anyway because you're not going to have to prove it. But the limit as x goes to 0 of sine x over x is 1. You can prove that using the squeeze theorem. Not quite in the same way. It's a little more complicated than this one, but you can prove it. And then also the limit as x goes to 0 of cosine x minus 1 over x equals 0. You won't use this one nearly as much as that one. The important thing with this, though, is that this doesn't just apply to x over sine x over x. It applies to sine of anything over that same thing. All right. The issue is this, whatever the sine is of, whatever's in here, has to match this, and then it'll be 1. Okay. So I had in graduate school, the professor that I teacher assisted for used to say sine of cow over cow. All right, it doesn't matter what's here, they just have to match. Okay, now the deal is you can't change this. It's inside of the sine function, and sine is a function. You can't take things inside and outside of that parentheses. You can change this. All right, so you want to figure out how to change that. So this first example is a pretty basic one. We have the limit of sine 15x, and this would be sine of 15x. I'm usually lazy and don't put the parentheses around it, over x. The deal is we want this to be 15x to use the theorem. So how do we get this to be 15x? We multiply by 15. If we multiply by 15 on the bottom, we also have to multiply by 15 on the top. And again, communication is important. You do need to show this work. So you'll get to the point where you're like, I already know what this is. Why do I have to show all this work? Because you have to be able to communicate the math. And yes, you have to write the limit every time. That's annoying. The theorem says that this, since they now match, equals 1. So 15 times 1 is 15. All right. Let's see. This one, oh, I should have done this a different way. Let's do this one. All right, sine of x cubed. Okay, we want these two to match, so we want this to be x cubed. So how are we going to get that to be x cubed? We're going to have to multiply by x squared. And if we multiply by x squared on the bottom, we also have to multiply by it on the top. So what we get is x squared sine of x cubed all over x cubed. I wanted to do a different example, but that's okay. So then this, by our theorem, equals 1. X squared times 1 is x squared. Plug in 0, we get 0. Okay, so we did all that work to still get 0. By the way, this theorem also works upside down. So if you have x over sine x, it still equals 1. So on the one that you're going to try, it still works. You just have to get these two things to match. All right, the last one we're going to do is the limit as x goes to 0 of tangent x over x. So we don't have a theorem about tangent, so we need to do something else with this. Although once we're done with this problem, we will have a theorem about tangent because we will have proven it. We need to write this with sines and cosines, otherwise we can't do it. So tangent is, what I'm going to do first, so that x doesn't get in the way, I'm going to pull that x out. So I'm going to write this as tangent of x times 1 over x. You can do that. You can just pull that out, but you have to have a 1 in the numerator. All right, so I just pulled the tangent out of the numerator, I guess, whichever way you want to think of it. So then we want to write tangent as sine over cosine. So sine x over cosine x. And we still have that 1 over x. Now we can kind of rearrange things. It's all multiplied, so you can kind of just rearrange things. We're going to have sine x over x times 1 over cosine x. So I'm just flip-flopping these two. It's multiplied. It's okay. Multiplication is commutative. We can change things around. All right, our theorem says that this equals 1. And so we're just left with the limit as x goes to 0 of 1 over cosine of x. So we plug in 0, cosine of 0 is 1. So that whole thing equals 1. So we have now just proven that what we're doing with sine, this theorem for sine, also works for tangent. All right, it doesn't work for cosine. Cosine is completely different. All right, it has to be cosine minus 1 over x. But also works for tangent. So if you had tangent of 15x over x, you could do the same thing that you're doing for sine. All right, and we proved it right here. All right, it isn't part of the theorem, but we did prove it. So you could use that.